We're going to be doing a bit of quantum RAM today. Basically, it's been too much around lately that I just think it's worth. Did I bookmark this? I think I didn't bookmark it. I have so many things that I would like to work on, and I'm just kind of. Maybe you just go to the profile and go and check the. Oh yeah, this. No, it was a quantum. It was a quantum bullshit detector thingy. Oh, maybe it was a. Was it quantum bullshit? It was a. Oh yeah. This qRAM bullshit, and I was like, wait a second, yeah. The thing is, I've seen these before. qRAM, Q#. Was it in GitHub? Yeah, it's a library for Q# for implementing quantum. Is this? Yeah, it's for Q#. Yeah, it's by Crazy for Pi is there. Different proposals for memory for quantum computers, also commonly called qRAM. Want to learn more about qRAM? Check out the primary memory for quantum computers on in our doc. So maybe I'll start here. So there's an actual PDF. Okay, it's been continuously edited. But maybe that's a good starting point to go through first, because basically they just go ahead like here. So the quantum BS detector goes and says like qRAM is bullshit. And I was like, and Guillaume is like, yup. And I was like, okay, I definitely got to ask. And I got a lot of answers. I haven't gone through them. Like maybe I should go through them quick, like sort of in detail, right? Like, because Craig says the bullshit is qRAM being too cheap to matter when comparing quantum to classical. Really, every qubit in qRAM needs active error correction. Suppose it takes 1 CPU per qubit. Repurposing those CPUs to just solve the problem directly often removes qRAM-based quantum advantages. So they're not saying the idea is BS, but like it's not doable in a way that it's actually kind of enabling for the quantum advantage to be there. Another way to think about it is that qRAM is a tricky way to smuggle in ON magic state factories, but then ignore the cost of those magic state factories and the resource estimate. Magic state factories are expensive, so this is misleading. So Craig keeps mentioning magic state stuff, and I remember his blog has made some mention. Well, something with P-gates, I think, or with magic state. Oh, look at these. So there's something in here, magic state. That's the only thing he talks about. That's the only place where he talks about these, or? Oh, there's actually a paper. Okay, where magic state factory constructions are producing CCZ states and T states. For the CCZ factory, we applied the surface code lattice. He mentioned that once, but I forgot what a magic state is, actually. What a magic state. Oh yeah, magic state distillation. He does mention these as well. Sorry, guys. I need to actually have something that reminds me what time it is. Something that's called a clock. Yeah. It's a process that takes multiple noisy quantum states and outputs a smaller number of more reliable quantum states. It's considered by many experts to be one of the leading proposals for achieving fault-tolerant quantum computation. It takes multiple noisy quantum states and outputs a smaller number of more reliable quantum states. Magic state distillation has also been used to argue that quantum contextuality may be the magic ingredient responsible for the power of quantum computers. Okay, so what is this? Oh, going deep already. There's a feature of the phenomenology of quantum mechanics whereby measurements of quantum observables cannot simply be thought of as revealing pre-existing values. Any attempt to do so in a realistic hidden variable theory leads to values that are dependent upon the choice of the other variables, which are simultaneously measured. More formally, the measurement result of a quantum observable is dependent upon which other commuting observables are within the same measurement set. Contextuality was first demonstrated to be a feature of quantum phenomenology by Bell, Kohn-Specker theorem. The study of contextuality has developed into a major topic of interest in quantum foundations as the phenomenon crystallizes certain non-classical and counterintuitive aspects of quantum theory. Never heard of quantum contextuality. Never heard of these. Okay, let's just go back for a second. So magic state distillation is this idea that you take multiple noisy states and you kind of make a more fault tolerant one. It is known that some quantum operations can be perfectly simulated in polynomial time on a probabilistic classical computer. In order to achieve universal quantum computation, a quantum computer must be able to perform operations outside this set. Magic state distillation achieves this in principle by concentrating the usefulness of imperfect resources represented by mixed states into states that are conducive for performing operations that are difficult to simulate classically. A variety of magic state distillation routines with various advantages have been proposed. Stabilizer formalism. So magic states are purified from n copies of a mixed state. Okay, I think that's getting too deep for now. But there's this. I should come back to this at some point. Why am I here though? Oh yeah. So magic state factories, okay, but then ignore the cost of those magic state factories in the resource estimate. Probably as in that you're pulling in those magic states from the qRAM, if I understand this correctly. Magic state factories are expensive, so this is misleading. It's not unreasonable to imagine a specialized hardware device that handles memory lookups under superposition. It's unreasonable to imagine it will be 1,000 times cheaper than general compute, without also assuming huge improvements over known fault tolerance techniques. Okay. And then there's a bunch of other answers from Guillaume where he's like, it's not going to be worth implementing for a very long time, if ever. The theoretical studies have been interesting, but they are just that. An interesting object for theoretical QC, though shouldn't be discussed in applied QC, really, in my opinion, as it cannot be implemented in real life. Or rather, if you spend the effort to error correct it, you're basically, I don't know what SOL means in terms of your supposed power draw advantage. Furthermore, many algorithms that leverage qRAM have been dequantized by Ewing-Tang and have lost their exponential gain. Finally, while it's easy to churn out papers that have nice proofs with unrealistic oracle assumptions that get accepted in prestigious conferences, it should not be the focus of the field in applied QC, the industry. Okay, fair enough. Fair enough. You're getting a lot of hearts from me today. Yeah, I mean, everything that you guys reply, everything that you guys this has been so helpful. It's been really so helpful. Just going to retweet the whole thing and do the same with Greg. I think it just doesn't help me. It helps many other people out there as well that are exploring these topics. And yeah, what is these though? qRAM might be years away, but QC-ware data loaders are available with new release of Forge. You can make your own data loading scheme for free in TensorFlow Quantum. We have a whole pipeline for quantum data sets. Furthermore, I would emphasize there's still no evidence that embedding data into the parameters of QNN should yield an advantage for classical QML. Interesting. Should probably read these through. But this QC, where I haven't really heard a lot about them. What is machine learning? So they're saying that they have a way to qRAM hardware, qRAM inspired circuit. Cubic count required 1,000, over 1,000, Forge parallel data loader, 1,000 circuit depth, 10 existing hardware. Like you can, how can 100 qubits be like existing? Oh, you mean it's 1 qubit per data? Or Forge optimized data loader, 100, 100, and 1,000. Existing hardware, low qubit count, lower depth. I'd love to play with this though. I'd love to try this, see if it's true. Anyway, so we're here to explore more about what the qRAM thing is, because it popped up in many other recent papers that we discussed in the paper club in the Discord server. It popped up in some of the conversations with people from the Discord, and then I came across this also because it's supported by the Unitary Fund, and it's a nice animation. Okay, but let's take a look. So this seems to be a okay. So the qRAM library for Q#. There are many proposals, each have different trade-offs, and currently come up a lot in quantum machine learning applications. So we want to better understand the costs and benefits of different qRAM implementations in quantum machine learning as well as quantum computing more generally. So this library will help achieve these goals by giving us a concrete way to measure the resources each approach takes. Choosing to use in Q#, I mean, if the reason of the whole thing here is to try to understand what the costs are, then that can be an interesting project to keep an eye on. Amir is also involved. He's on the server. Let's go through the primer, though. Quantum RAM has gained some notoriety in the past few years, and attitudes toward it depend quite heavily on the circles you're running. The goal of this set of notes is to provide a general overview of the subject, as well as discuss some very specific implementations. It is meant to be a companion to the qRAM libraries we're writing. Cite the repo. Yeah, okay. So do I need a qRAM? Sometimes. You'll need a qRAM or some more general means of quantum state preparation in quantum machine learning algorithms that require you to load in classical data or query an oracle that returns classical data. I've heard a number of stories of people working on QML being actively discouraged from doing so because QML won't work without a qRAM. That's just not true because many QML algorithms do not need qRAM. Now, whether or not they yield any quantum advantage is a separate question. Can we design an efficient qRAM? Maybe. In this primer, we'll take a look at proposals that will in principle run in polynomial depth, and others that scale far worse. There are some very interesting qubit time trade-offs one can explore, in particular if the data being stored has some sort of underlying structure. Regardless, even if we can design an efficient circuit, we'd also like something that is efficient in a fault-tolerant setting, and this is potentially very expensive. Can I build one? Maybe. No one has actually done so, but there are a handful of hardware proposals that will be discussed in more detail somewhere later in the document. Brief history, encoding classical data in quantum computer, basis encoding, giveaway with the basis encoding, quantum RAM ROM, query as bits in super. Okay, so this is it's pretty early stage though. Query Query as bits in superposition. Query as phase in superposition. Applications to Grover. Quantum state preparation, amplitude encoding. Given some vector A, create a quantum state where each of those elements is, it's encoded in the amplitude. Discuss how this relies on having a qRAM as an underlying subroutine. Packet Brigade Quantum RAM. Architectures for qRAM began to emerge roughly a decade ago with the Packet Brigade RAM model. The particular storage model of RAM that is used is a binary tree where 2 to the power of n bits are located at the leaves of an n-level binary tree. As depicted in whatever, we'll first take a graphical look at the Packet Brigade algorithm. Following these, we'll see it modeled as a quantum circuit. That's probably what's in here, right? So, query location. What is it doing? So it comes in as a 1. It goes right. Then it sends a 0. It goes left. Then this is a 1. And it picks that 101. Oh, it picks that 1 that's in there. Okay, the idea though would be that you can probably, if you send it a plus state, it will just go both right and left. So you can, in theory, but how can these translate into a circuit at all? And what's the... I feel really disconnected to the concept right now. I don't really know where to take that. Like, okay, increasing efficiency of RAM with Packet Brigade. Let's just go forward. The motivation for Packet Brigade lies in a less efficient type of RAM denoted as Fennel Ram. In the Fennel Ram, the nodes of these three are transistors that, depending on their state, will route incoming current left or right towards the next level of the tree. Each level of the tree is associated to an address bit. The value of the address bit can set a level-specific switch that tells it all transistors in the level to send current left or send current right. This is shown in the has the effect of creating only one complete path from the root tree to the leaf. The issue with Fennel Ram in this form is its efficiency for an n-bit address where turning to the power of n-1 transistors, while only n of them are involved in the actual query. A further issue arises if we make a direct translation into qubits. Suppose that we replace each node of the tree with a qubit that can let its 0 state indicate a route left and 1 route right. When we go to initialize the qubits to create a path, the kth address qubit will have to couple with 2 to the power of k node qubits. This is a very precarious superposition, especially in an era where coherent times are low and multi-qubit operations are significantly noisier than single qubit ones. The Packet Brigade model is an improvement that addresses both of these issues. Rather than using qubits at each node, we use qtrees, or three-state systems. In what follows, we will discuss the quantum case, but the methodology is the same for the classical case. It uses trees instead of bits. In the top in the binary tree, each node sits a qtree whose state is wait, left or right. All the qtrees begin in wait. To perform a okay. What am I looking at? To perform a query, address qubits are introduced to the tree one by one. The kth address qubit will affect an operation in the kth level of the tree to carve a path to the desired memory cell. The key to the bucket Brigade model is to define a unitary transformation that allows address qubits to alter the state of the qubit node depending on their own state. Specifically, we need to find some unitary that transforms. Okay, I get it. Okay, so each of those actions are operations. So a 0 times weight into S left, I don't know what S is, and 1 times weight equals S right. Where S refers to some arbitrary state, we don't particularly care what it is, as U is reversible and will be undone later on. Okay. So this is, okay, so that's the idea. Like each of those points in the tree would then correspond to a unitary gate that basically, when you give it a 0 and it's in the wait state, it will switch it, turn it to left, and then we don't care what's in here where the 0 used to be. Okay. When the bottom half describes how the contents of memory are retrieved. Quantum bus. So that's a bus. What comes down here left at the end? That's a bus. Okay. Okay, I guess, and it comes with a 0 and it just picks the state in here. Where was I? Couples to a desired memory cell to gather data and is reflected back the way it came. As it passes upwards through the tree, it reinitializes the qubits back to weight by running U-dagger. Note that such an algorithm allows us to query in superposition, as all operations are unitary. To see how efficiency is improved, let's count the number of unitary operations. The first address qubit performs one operation by coupling with the root qubit. The second qubit performs 2, the root qubit, and then the qubit in the second layer. The third performs 3, and so on. This means that to set the qubit takes n times n plus 1 divided by 2 operations. More succinctly, it's a square, like it's a quadratic. Okay. The bus qubit performs only 2 times n plus 1 operations, which does not worsen this complexity. This is a polynomial. As this polynomial in the address bit size, the bucket Brigade qRAM appears to be efficient. It is also claimed that since only n of the qubits are involved in the query rather than to the power of n minus 1, it's potentially possible to get away with a worse error rate and leave idle qubits uncorrected. Okay. What happens when we query in superposition? I don't have a satisfactory answer for this. The claimed advantage comes partially from the fact that we only need to tinker with n of the qubits, but if we query in superposition, don't we still have to handle all? Yeah. Can we actually get away without error correction? Potentially. It has been shown that in cases where there are super polynomial amount of queries to the qRAM, for example, in Grover's algorithm, the error rate must be super polynomially small, in which case we'll in fact need error correction. That said, in situations where the number of queries is small, it may be possible to get away without it, in which case Bucket Brigade provides a substantial improvement in the number of operations that must be performed. So the point is that to be able to, index 8 cells, so basically to be able to, have a 3 3-bit addresses. You have 1, 2, 3, 4, 5, 6, 7. Yeah, that's 2 to the power of n minus 1. Okay, and that's exponential, so I get it. So the point is, and maybe that's kind of the question that they left, that they're leaving open in here, is kind of what Guillaume and Craig are saying. It's like the actual advantage is the superposition, right? So if the superposition axis. And the thing is, if you access in superposition, then you're going to need to kind of, it goes both left and right. And so basically you need an exponential number of qubits, which is bad, and you need to error correct them all, which is bad. At least for this type of protocol. I would guess, and this kind of, it's maybe a circuit. I don't know. How would this be implemented, really? BigQuery circuit model. While conceptually simple, the Bucket Brigade model as described in the previous section does not lend itself very well to implementation in our present-day machines. For one, it requires both qubits and qubits. Furthermore, the operations are not specified in the usual parlance of the circuit model. How to implement this U and the routing. The circuit model for Bucket Brigade was presented in, was it Bucket Brigade qRAM? Okay. There's actually some circuits in here. Okay, interesting. Fennel query, Fennel methods. Fennel. I don't want to zoom like these though. I probably don't have any other option. Two Toffoli gates. Let's go back to the beginning. Quantum random access memory, blah blah blah. A Bucket Brigade circuit consisting of C nodes and Toffoli gates. The control gates from the diagram use add for controls and X for target wires. So this is the address. I guess those are the address qubits. That's in the query and the fan in. I don't know what B would be. Okay, the address wires are named A. Okay, the memory cells holding single bits are M. Yeah, that's what I assumed. So those are the memory cells. The classical bits stored on the wires determine which memory wires to read. So these are the address, sort of the intermediate addresses or something. The classical bits stored on the wires B determine which memory wires to read. So Okay, so if the A0 is 1, then it's weird that A0 is placed here, not here. But so it's a control node, and so we're turning these on. And that's the target. Okay, and so what this is saying is then the query is using these and then using the bits in the memory. You're just reading one bit, right? So how are you going to create a superposition? How is these wire, like how is this circuit gonna like enable superposition access? Okay, because if you have, so if this is in superposition, then this is gonna get entangled here. And then this is gonna get entangled here. And so that should actually give you a superposition as long as you. So let's say if you're, I feel I'm pretty slow today. if this is the address, let's say just 1 for address, and then there's this other one, right? This is memory, and let's say memory is 1, right? And then we've got like the target qubit is here. So we want an amplitude display in here. And then what this does is the C naught, and then these with the actual memory cell, like these. That goes like that. So if I have a 1, I get a 1. If I have a plus, assuming that I uncompute these, yeah, that's crap. I don't get it how you can get a superposition. I'm just not seeing it. Okay, you don't uncompute these. Sorry, you don't uncompute these, you just uncompute these. But still that's in here, right? Still that is still in superposition, that is still entangled with the address. Is it? Yeah. Right, right. So what I did is I think this is not working again. Oh well, if I actually plugged the pen, then it will make more sense, right? For this to actually work. Oh God, it's in the top screen now. I want this to be in the bottom. No. Is this doing anything? I want monitor 1. Good. There we go. So I was just playing with these part. So this gate here, right? This one. And then on computing, so ignoring the rest. But it's not, doesn't seem like it does what I expected it to do. But okay. I mean, it's not on computing these, so it's still like, it's still entangled to these. If I do these, if I pause select, then if I measure and pause select, then it's just anyway. Are there any other parallel Clifford T buckets, parallel as I, okay, no. Should probably read through these, but I'm not going to do this now. I'm going to go ahead with these. BigQuery circuit model. While conceptually simple devices described in the previous section does not lend itself. I will read these. A circuit model for the is presented contains the redrawn version of the circuit in order and that highlight the structure of the algorithm as well as the patterns of gates that are used to perform the query. The bucket Brigade model consists of 4 registers of qubits. So they explain, okay, so an address register A of n qubits, and a memory register M with 2 to the power of n qubits containing the stored values, and an auxiliary register tau with 2 to the power of n qubits to trigger readout of the memory register. An output register. Okay, so this is exactly what I just read here, right? Like this is the, so the tau is the B in here. So basically you need to duplicate these because like the address basically is going to set up which ones you want to read. But then in order to actually read them, you need to thoughtfully, you need to control it for the actual memory cell so you get the right target value. So that is basically what I read. Resource estimation. Okay, let's take a look at these. One of the primary reasons for designing qRAM is to get better resource estimation for qRAM circuits using the functionality afforded to us by both the resource estimator and the Toffoli simulator. Note that all the gates in the Toffolis, and so bucket Brigade qRAMs are essentially really just fancy Boolean circuits. Plenty of optimization tools exist for Boolean circuits, and so we anticipate that we'll be able to do reasonably well. But first, let's do some resource estimation by hand to get an idea of the worst we can expect. We'll do resource estimation at the logical level, not delve into the fault-tolerant level and estimate things like physical qubits and time required. Instead, we'll focus on the following set of parameters. Yeah, okay, but I get it. So if we're not doing anything, if we're just staying at the fault-tolerant level, that's already a whole different discussion. Number of qubits and Q, circuit depth, T count, CNOT count, non-CNOT Clifford count. Also, this is a little bit different though. Okay, so tau is a bit different here. Memory. I like how you count the memory 0001, 1011, and you start with A1 here. Okay, so these are just fancy. Yeah. And then at the end, okay, so this kind of, this circuit makes more sense. And then at the end, you're, what is the one used for here though? it essentially it seems like an additional control. Prek because it could fit the Q1 qubit address to memory cells. Top left. Okay, that is 1 qubit address. Okay, cool. Actually, let's go ahead and try this in Quirk. So what does it do? So it's the address, and then we have tau. It has this one set to 1, and then what it get the pen. And then so what it does is, let's get rid of these guys, and then it has a you know what? We'll just put it like this and go straight here. Oh, come on. So we're trying to do these. Damn shitty windows. Okay, so we're doing these, then we're doing no, so it's going here, then it's going here. Then it goes here and it goes to M, so this is the M register, and then we're doing these like that. Okay, so this is basically, so there's the two memory registers are these ones. This is memory. So if I'm gonna store say a 1 here and a 0 here, and if I access both addresses in superposition, I want to see. Yeah, but again, it's stuff is entangled. So what's the point in these? Like I gotta keep everything else stable. Otherwise, it just goes to crap. Like I get it. If my address is 0, then I get a 0 because that's what I have here. If my address is 1, I get a 1. I can also store here a 1 and here a 1. I should be getting a 1 no matter what. Yeah. So this works. But as soon as you add a superposition access, which is supposed to be the whole deal here, we get an entangled state, and this is well, we get an entangled state if we have memory set up like that, right? Like when you have a 0 and a 1, so you want a superposition of 0s and 1s, but it's everything entangled, and so it's not entangled with memory. That's interesting. It's entangled with the addresses and the auxiliary. Wait a second. The address and the two auxiliary qubits. Yeah. Okay. But maybe that's not a problem. I don't know. Resource estimation. T-tabs. Before beginning, we need to make some assumptions. All of the gates in the BB circuit are either C-naughts or Toffleys. Assuming we choose the typical universal gate Clifford plus T, it is necessary to further decompose Toffleys into elementary gates. These are a number, the number of ways of doing so, and they differ. They overcard a total of 7 gates. Okay, so now we're gonna count do some estimation, count all this stuff. It just requires an exponential number of qubits. I think that should kill the whole argument, right? Like, and not only that, like it's an exponential number Yeah, of just gates. Multi-qubit output. Let us now perform the same analysis for a situation where the memory cells may store multiple beats. Well, suppose the addresses are still n beats, but store k beats each. Improving T-depth with the CCZ gate. Okay. Control Z gate. Yeah. Okay, I get it. So if you use these to composition, then you're gonna get less T gates that you need to do. And what is the outcome of these? What is the outcome of these though? Okay, there's no, they haven't done the count. But it's, I don't think it's significantly smaller. Phase query circuit model. So in some situations, most notably in Grover's algorithm, one is concerned with retrieving the memory contents not in bit form, but as a phase. Yeah, because you have the oracle, exactly. So the address I basically, okay, so what this is saying is if you're like, if you want to know what's in like address 001, let's assume it's the value. Let's assume it's the value 001. You want this element minused in the oracle as a result of the oracle. In particular, all that must be done is to start with the target in state one, replace the TOEFL with CCZs, and then, yeah, okay. So all you do probably is just change these things, and then those things basically are just Z gates, so they just flip the faces of the stuff that you want to get, and there you go. But still, you're not going over the constraint that you need like an exponential amount of qubits. Should I turn my head or the screen? Whoa, whoa, whoa. And that's just to address 3 bits of like 3. Wow. Like, so 8 cells, right? That's nuts. But still, this doesn't seem to address like what I just kind of said, right? Like, so with these things being entangled. It feels like, I mean, you're with this kind of circuit, you end up just, your target is entangled with the address register. And so that seems bad because then you can't just reuse the addresses, right? Like, it means you got to do whatever you want with what you fetched before you change the address. Because if now I go and say, mm, well, I mean, if one of those things gets just measured, then it just makes it more delicate, right? It's still, you can't use that. Like, it's just entangled. And what would it mean to say then you want, for example, something like these address. Yeah, essentially, it's a bit like teleportation, kind of. Not teleportation, sorry. Super dense coding, no, also not. No, it's just, it's like a swap, like a huge swap. Yeah. Is it? So what is it doing if it's in plus? Let's go step by step. No. So basically, it turns this into 1, and it will just switch this guy off. Not off, it'll be 50-50, right? But it will be entangled, exactly. This is because we've done the journey down here with a plus state in the control, and then we're kind of going up again. Yeah, okay. So basically, that gets into these. Okay, so we're getting half of it, and we're getting literally half of one and half of the other. That's what this is doing. Yeah, but anyway, it's okay. So I now I understand a bit better what this all thing means. I understand the circuit seems to be a simple concept, but it just seems to be indeed just unfeasible. At least that way of implementing it. It just requires an exponential amount of qubits. Not only that, I mean, it's like, yeah, twice, right? Like, okay, twice doesn't really make it worse, but yeah. Code example. Query measure qRAM, memory, qRAM, address, int. So I still don't get. I'm still a bit confused. Maybe I'm just missing something again. It feels it's maybe a bit basic, but how would that like? It entangles the thing, right? That's bothering me right now. Maybe I'm missing something. It's just entangled. So I can do something with it. And then I got to disentangle at the end, right? Like, so basically, okay, but not oh, not these. I got to only disentangle with these guys. Now it's fully disentangled because I've uncomputed these. So, but in here I can do whatever I want with it. Like, does it? Why does Quirk still? Why does Quirk tells you it's incoherent here and it cannot show you the phases because of the entanglement? Because that State basically, so you do have a 0 plus 1 state, right? Okay, so you do have a 0 plus 1 state here. It's just that it's entangled with all the other mess. But if you think about it, like the probabilities of that last qubit are 50% of being 0 or 1, as long as nothing happens to the other qubits. But you need to uncompute everything else later. Okay, I think it's enough for that for now. I was expecting something a bit more. It's just obviously complex. It's obviously expensive. Let's put it this way, right? It's obviously expensive. Yeah, well, think about like 30. Think about like 32 like beat addresses or something like these. Like how big are the addresses you can have? Like, yeah, that seems yeah, I don't know what to say. I expected maybe a bit more of a, aha, okay, that's why it doesn't make sense, or that's why, like, I don't know, it just seems a naive approach, at least to me, at least these version of it. But assuming like now, right? Like if you assuming fault tolerance and assuming you can build quantum computers with like millions of qubits, maybe you can build some qRAMs this way. I don't know. Anyway, that's it. I think there's nothing else in here, to be honest. I thought that would be there would be something else in here. But it seems it's really early stage, so I'll definitely revisit that. I'll definitely revisit that in the future. Cool.